So now it's time for the LTTng status update for 2018. Hi everyone, I'm Mathieu Desnoyers. I'm CEO of EfficiOS. So it's very good to have everyone here today. I hope you have a good time at this Racing Summit. So if we have a look at what has been done on the LTTng project in the past year, so we spent quite a lot of time, and actually I personally spent quite a lot of time pushing modifications to the Linux kernel to actually improve the performance of the user space tracer of LTTng, so LTTng USD. So one of those improvements is the Membarrier system call, which I contributed to the Linux kernel in 2010. So it basically allows algorithms where you have matching sets of matching barriers to which consist of a fast path and a slow path. So by basically slowing down the slow path and at that point issuing memory barriers on all the relevant cores, you can actually get away with removing the actual memory barrier instruction on the fast path and just have a simple compiler barrier. If we look at what has been recently contributed by myself, so the private explicit command of Membarrier was merged in 4.14 version of the Linux kernel. I renamed the shared Membarrier to a global, so the namespacing was better. I added a global expedited Membarrier, which is now used in libURCU, which is used by LTTng USD for low-level synchronization to speed up the fast path of tracing. And I did some work as well that's not related to tracing, but to speed up, to allow JITs, just-in-time compilers or engines, to reclaim their memory in a way that is really portable. So it's basically to have a way to flush the state of all cores on the system before memory gets reclaimed. So the other contribution that was merged early this summer is the Restartable Sequences system call. So I did a talk on Monday at the Open Source Summit about this. So it's a new system call that accelerates user space operations on per-CPU data. And amongst the use cases it covers, there are many, but the one we care about here is to speed up the LTTng USD ring buffer. So rather than having to, basically those are per-CPU ring buffers, and rather than having to call the glibc get CPU, which calls the kernel VDSO to get the current CPU number, which, let's say on x86-64 does a LSL instruction, that sums up to quite many cycles. RSEC really has a facility that allows to keep always an updated value in the TLS area that's registered to the kernel, an updated value of the current CPU number. So reading that CPU number can be done with a simple load from a TLS area. Which is really, really fast. The other thing that RSEC speeds up for LTTng USD is the atomic operation. We need to reserve space in the ring buffer and to commit in the ring buffer. In user space, one thing you cannot do is disable preemption. So by the time you have fetched the current CPU number and you know on which data you want to work on, you might be migrated at any point in time. And then you can be updating the per-CPU data from the wrong CPU. And of course, the right CPU might also be touching it. So you basically, even if you work on per-CPU data, you need to be synchronized against concurrent accesses in user space, which means a lock prefix instruction on Intel architectures, or building stored conditional on PowerPC ARM kind of architecture. So our Restartable Sequences allows a critical section of code to be executed atomically with respect to other things on the same CPU that would be affecting the user space data. So preemption, for instance, signal delivery. So that has been contributed. We have good performance. So this is an example of the speed up we get for ARM32 and x86-64. So if we look at x86, so from 117 nanoseconds per operation of recording an event with a 32-bit header, 32-bit payload into the per CPU buffers, we go down to 98 nanoseconds per operation. And at this point, I mean, getting those improvements starts to be a big improvement for the LTTng UST tracer, which has been tremendously optimized over the years. So that's the point where we are at, where we need to create new kernel facilities to improve the speed of the user space tracer. And well, by doing so, those facilities can be generally used by memory allocators, RCU synchronization libraries, and so on. So, the upstreaming status, so it was merged in 4.18, it was wired up for x86, PowerPC, MIPS, and ARM only 32-bit. In 4.19, it was wired up for ARM 64 and S390, both 32-bit and 64-bit. The ongoing work I'm currently doing on Restartable Sequences, so librsec, so it's a library that provides helpers to create the usual operations to use, do a compare and exchange on per CPU data, for instance. So rather than having to create the per architecture assembly code that is needed to do those operations, you can just use headers from the library. I'm also doing work on the glibc side to make the registration and unregistration of restartable sequences automated. So at thread start and thread exit, as well as NPTL library initialization. And I'm also working on a new system called the CPU version vector, which complements RSec in a way that where the use cases that RSec does not support well, CPU-LT can be used. It's a bit slower, it is a system call that needs to be invoked to do it, but it allows the kernel to do the operations that RSec cannot do. So now, LTTng. The new features. So currently LTTng 2.11, so we are very close to the final release. We are in release candidate stage. So the main major feature that it introduced is session rotation. And I will go in more detail in the coming slides. So it has dynamic instrumentation, filtering on array and sequence of integers for the user space and kernel tracer, bitwise operators for filtering, and sampling the callstacks of user space and kernel from the kernel tracer. So first, session rotation. So it allows splitting. So let's say you want to gather a trace. You typically set up a trace session, you enable whatever you want, and then you typically either use the live mode and live consumption of those traces, or you write those traces to a media, and after the fact, after you have stopped tracing, then you can consume it. So the first approach, the live approach, was designed really more for, I would say, scenarios with low throughput of trace data, where you see things in a console. The other scenario, if you have a long run, let's say you have a test run of 12 hours, I mean, it takes a while before you can start doing computation and analysis on the data. So we have created something in between. This is inspired from log rotation, where basically, periodically, you will want to stop writing into a log file and then start writing into a new one, and either compress the old file, or I mean, that old file is closed. So we have done the same for traces. It's a bit more complicated under the hood, but the idea is, so we have a set of streams that are being written to. Then we can, either the user requests to start a rotation, or a timer does it, or it can be also size-based. And then what that rotation does is it will start writing into a new set of files, into a different subdirectory, and then it will be able to optionally notify an external application that the old files are done being written to at some point in time. So, and at that point, it is safe to read the data from the previous chunk, so what has just been completed, which enables many interesting use cases. The main use case it enables is pipelining and sharding of analysis, so scaling out your trace data analysis. So currently, all the approaches we have really require to basically on a single node do the analysis in sequence of all the trace log, either live or from this medium. Here, what this allows to do is once a chunk is completed, you can push it to an analysis node, and then whenever the following chunk is completed, you can push it to a different analysis node. And basically those analysis, I mean, if you do simple, I would say punctual aggregation, counting events or things like that, I mean, that's trivial to translate into a MapReduce algorithm. So you basically count locally, and then in the end, you sum up those counts. So you can see Jeremy Gallardo's talk. It's been filmed, so you could see it on the open source site content pretty soon, I guess. So he discussed cases where if you have state that is generated, so he talked about file descriptors, mapping file descriptors to their actual file names that were opened. So there's a state like this which can span over many chunks. So the idea there is really you can create an analysis that will tolerate having incomplete data, and then at the map phase, and then and everything that is available locally in a chunk just gets all stitched up right away. And then in a reduce phase, then you can stitch up what is left. And there should be very few operations to do that. So this is a really interesting area. It allows also encryption, compression, cleanup of all chunks, integration with external message bus tools. Another features that came into LTTng 2.11 is dynamic instrumentation. So the whole idea there is to be able to add trace points without having to recompile or restart the process. So I mean, we have been doing a lot of experiments in that area in the past years. But the approach we chose to do as an initial step is really just to allow integration with uprobes. So it's a kernel facility that allows instrumenting user space with breakpoints. And the way we're integrating that is we're integrating it so that it's going to write into the LTTng modules ring buffer. So the kernel tracer is going to store the trace data that is generated from the uprobe instrumentation. So currently we support two instrumentation point types. So working on ELF symbols, so function entry, and working on system tap SDT probe points, but only the ones without semaphores, because that would require more work at the user space level. And the good news about this is, I mean, ELF symbols, I mean, that's already available everywhere, and the system tap SDT probe points are already available in many open source projects out there. But how to enable it? So even though it is a user space probe, you have to talk to the user space trace kernel tracer, to the LTTng kernel tracer to enable the user space probe. Then you specify the type of probe. In this case, it would be ELF, the path to the binary, and then a symbol with the event name. So the limitation of that approach, it's slower than LTTng USD because it's context switches, or it changes privilege level to the kernel to do the tracing through a breakpoint. And currently we don't record any trace point data, so that is future work. So another feature we added is filtering on array and sequence of integers. So the idea is we can basically filter out based on the content of an array or sequence. So this is very good for protocol matching, for header matching of whatever is in payload of events. So it allows defining filter using indexes in sequence. So those are two examples here. So next one. So while doing that, we noticed that bitwise operators would be really good. So not being able to just say, I want to target the following values of those fields or those ranges, but also be able to figure out, okay, if I do a bitwise operator and only take a mask of that field, I would like to see the values between this and this. So this is really useful, again, for protocol matching. And this filtering is done in LTTng UST and LTTng modules, the two tracers, at runtime. before writing trace data to the ring buffers. Sampling the Callstacks. So in the kernel tracer, at the moment only, so we added this facility to allow sampling the kernel and user space Callstack as an optional context. So the user can specify that they want to add a context to the kernel or user space tracer, specify a user Callstack or a kernel Callstack, and the main use case there that we all enjoy is sampling the user space Callstacks whenever you enter into a system call. This is really useful to figure out who's responsible or what code is responsible at the application level to invoke that system call. However, one limitation at the moment for the user space Callstack is that it requires application and libraries to be built with frame pointers enabled to unroll the user space stacks. However, you will start, so let's say an application calls a library which invokes a system call. So the system call will know what instruction pointer called it. And then, but then if the library, or the first library in the stack that does not have frame pointers enabled is going to be the point where we will have to start iterating on the call stack. So you will not see what is underneath, even if the application was compiled with frame pointers. So you really need all the libraries that sit in this call stack to be compiled with frame pointers at the moment. So there will be future work that might allow not relying on frame pointers, but yeah, I mean that would be kernel infrastructure work that would be really interesting to tackle. I know that perf as a way to just grab the entire, I think it's 2 kilobytes worth of Callstack data and just dump it in their trace, so that later on at post-processing, they can figure out what was happening there, even if they don't have the frame pointers. However, considering that the LTTng tracer is meant to be used for high throughput tracing, we cannot afford to save 2 kilobyte worth of data for every event. It would really kill the ring buffer performance. So those are trade-offs. So upcoming for 2.12. We have the user ID tracker, so it can track user UID, GID, in addition to the PID tracker that we have. We have a fast LTTng clear that we plan on doing. So basically, let's say you have a trace session ongoing. You just want to clear the content of the buffers and the files on disk so that you can kind of start from a clean slate from that point in time without having to destroy your session and set up everything all over again. We have some enhancements for the relay daemon. One is to categorize trace hierarchy by session hostname, allow overriding current working directory, and doing a tracking of open file descriptor with a last recently used data structure that really allow kind of tracking those file descriptors. This is for cases where you basically cannot control the U-limit on your system on which you run the relay daemon, and you don't have any enough concurrently open file descriptor limit compared to the number of files you have to open on disk. So plan for 2019, dynamic snapshot and event notification. So that's a pretty cool feature where from a trace point, I'm saying trace point, but that could eventually be a K-probe or a U-probe or whatever instrumentation source. Rather than write, so there's filtering and then we write to disk whenever there's an event enabled. Here the plan is to trigger some action. So the action rather than writing to a ring buffer could be to send a notification that would be dispatched by the session daemon and then listened to by an external process. It could be sent over to various machines in the distributed setup so that we can grab a snapshot. So the idea there is really to, so writing in flight recorder mode and keeping the trace data in memory is pretty interesting, because then whenever you hit a key condition, you can grab that content, that very last time window, and connect that doing I/O to disk or to the network. But you usually need, today, you need an external program to do that, to trigger that. So here we want to really have built in the capability to allow users to specify that on specific tracing conditions, they want to trigger those kind of snapshots. And do that either locally or distribute that as well. Yeah, while I'm here, so Francis yesterday told me that I did some work in 2015 that I did not succeed in getting to work, which was to try to hook with ptrace for LTTng, so we could have a strace-alike behavior, follow children. So basically, you can spawn a program along with all its children and only trace that. So I had a prototype, but there were some really rough corners there. So that triggered me. So I think I worked too late last night, but I got it to work. So we might see it for perhaps to 12 or something like that, because now it really works well. So the idea will be that you'll be able to, I don't know how we will call it, perhaps LTTng trace or something like that, where you'll be able to spawn a process, and along with all its children, you'll be able to do kernel and user space tracing of only that hierarchy. And when that gets killed, all the tracing just goes away for that process hierarchy. So that will, I think, make it easier to use the LTTng tracer for many use cases. So that's what I have. Any questions?
For the strace, like process hierarchy tracing, are you still using ptrace?
So for the thing I just discussed, so I'm using ptrace just to get notified of process creation, exec, and exit for all the children processes. But I don't need to hook on every system call. I don't need to hook on all the rest. So it's the fork, vfork, there are one or two I'm forgetting. So it's really the basic ptrace functionality. But I don't need to use ptrace to listen to every system call. I don't get notified about that. So it's using ptrace without its overload.
One related feature would be tracing everything inside a container. That's a use case I would really like.
Yeah. That could be one way to do it. We have other plans as well for container tracing, but we are currently discussing with our customers about that. So yeah. Other questions? Thank you.